Okay, it's legal for me to start the lecture, so let me start. So I put in the chat a link for the class notes of the stuff I'm hoping to cover today. I might be able to cover a little bit more. We will see. I think if I cover this will be fine. So I want to state, before I start doing stuff, I want to state one of those lemmas, which is going to have a bunch of inequalities, which is going to be extremely useful throughout the course. I already stated some of those inequalities, but let me now state everything. And from this point on, whenever I use something from this lemma, I will just use it. I will not even say where it, I'll just mention that we already seen it. So this is in the class note. If you want to look in the note, it's lemma 811. So let me copy the interesting parts. So the first claim is that 1 plus x is smaller than e of x. This is very easy to see because e of x is just sum, I go from 0 to infinity of x to the I over I factorial, right? This is the Taylor expansion. So that's essentially where this approximation comes from. And also 1 minus x is smaller than e to the minus x. And both inequalities are true for any real number x. Okay, so this is, I use it already in the course several times. It's very useful. Okay, by the way, the class notes have the full proof of this lemma in excruciating detail. So if you want to see it, see it. It's just one of those things that so 1 to the 1 over n times n is smaller than e, right? So that's not very surprising because it follows immediately from the above inequality. Maybe more surprising is the fact that e is smaller or equal than 1 plus 1 over n to the n plus 1. Okay. So essentially it says that 1 over n to the n is a very good approximation to e. In particular, of course, this is a famous formula. So this is one way to compute E. It's not a very efficient way, but it's one way. Okay. We get something similar about 1 minus 1 over n to the n, right? It's smaller than 1 over e, of course. And this is smaller than 1 minus 1 over n to the n minus 1, right? So again, this is a very good approximation. Okay. And you need those estimates for the following formulas, which are really useful. So n factorial is larger equal than n over e to the power n. And the reason why I need all this stuff is because really what I want is this. For any k smaller or equal than n, I want a good estimate of the binomial coefficient. So it's smaller than n over k to the k. And this is smaller than n times e to the k to the k. Okay. So this is a pretty good estimate of the binomial coefficient. And it would be enough for a lot of our application. In particular, it would be good for the application we are going to do today. Questions about this before I go further into the darkness or into the light, whatever the case might be? Okay, so yesterday was my daughter's birthday, so I thought it would be a good opportunity to speak about the birthday paradox. And it's one of those paradoxes where, paradoxes like something that looks like a contradiction, but it's not really a contradiction. I assume you heard about it before, but let me just cover it again. So we're going to have n people, and we're interested in what size of n do we need to pick such that there will be two people with the same birthday, right? So let's oversimplify a bit. We have 364 days in the year, right? It depends, it's oscillate between 364 and 365, right? But let's just take 364. And the idea is that the birthdays are uniformly distributed, right? So the date that you're being born on is essentially a uniform random variable. Now, this turns out to be not quite correct. So if you're interested, you can look up on the internet. There are statistics about it, like how many people are born in the US and every day and so on. And this distribution is definitely not uniform. It's close to uniform, but not quite uniform. The reason is because a lot of the births nowadays are done with C-section, so they're scheduled, right? And nobody wants to be born on Christmas Eve or New Year's, so those days are not very popular, and so on. So there is non-uniformity, but for simplicity, let's assume that it is uniform because it's kind of correct. Although there were cases where I think in the late 70s there was a power cut in Manhattan for a day or something, and 9 months later there were a lot of babies. Anyway, so okay, so we want to estimate this. So let me maybe try to define it more formally. So we are going to have n random variable that are picked uniformly and randomly, uniformly, and independently from. So I'm going to use this notation to notate the set 1 to n. 1 to n, right? So, okay. So we are randomly picking the set, and now I'm going to ask then the expected number of collision is n choose 2 times 1 over n. Okay, what is a collision? A collision is two variable xi and xj that have the same value, right? For our people version, this would be that there are two people with the same birthday, right? So let's prove this. The proof is not very difficult. Right. I'm going to define a variable yij, which is 1 if and only if xi is equal to xj. Right. Now the trick to, we're interested of the yij is of course an indicator variable. So the probability that yij is equal to 1, this is equal to probability of xi equal to xj. Well, we do the regular trick, right? We pick xi and then we pick xj, right? We can pick them in any order we want. And if you do this, the probability that xj collide with xi, this probability is 1 over m, right? Okay, so now we are done, right? Because we want the expected number of collisions. Well, the number of collisions is I smaller than j of yij, right? We use linearity of expectation of yij. The yij, of course, all behave the same, right? So they're all equal to 1 over m. And of course, the number of elements in the summation is n choose 2, right? All the number of pairs that we have. So we get this. So this was easy. So far, nothing is too interesting, except that if you think about the case of people, I think for n equal 28, okay, n choose 2 in this case come out to a number slightly larger than 364, which in particular implies that the expected number of collisions, is going to be larger than 1 in this case, right? Namely, if you take a group of 28 people, we expect to have 2 people that have the same birthday, right? Which is kind of counterintuitive. So it seems, a priori, it seems very weird, right? It seems like that really should not be the truth, right? Questions about this? So the plan is to kind of dig deeper into this. Now, why we care about the birthday paradox? So as we will see later on, it's related to hashing and other problems, right? So in some sense, it gives us an insight about hashing and random processes and so on. And intuitively, this idea of allocating items, whenever an item comes, you want to allocate it a random number between 1 and n, is in fact very useful in practice, because think about situation where you have an internet router that gets packets, but it has several outgoing queues. And then, one natural way to do things is to just randomly assign the incoming packets to a random queue without checking the load, right? And the idea is that this would give you a pretty balanced partition of the workload, right? And then you can ask, for example, what's the probability that in a certain time a queue would get 2 jobs, right? There would be suddenly the queue would be non-empty, and then you might start having trouble. Okay, so that's why we care about it. It also, hopefully, as we will see later on, it's technically interesting. Okay, so this is kind of counterintuitive, right? You don't expect in a group of 28 people that would be 2 people that collide, but that turns out to be the truth. But maybe you're not very convinced by this, right? So let's try to give a stronger argument. So I'm going to be interested in the question of what's the probability. Okay, so I'm going to define events, right? So event I would be xi is different than all values in x1, x2 to xi minus 1, right? So the ith event is just that xi does not collide with any of the previous events, okay? Now, the problem is that bounding this event is going to be difficult. So we're going to look on a different event. Pi is going to be the event that there is no collusion, okay? So BI is the event that x1 to xi, there is no collusion, namely they are all distinct. Another way of saying it is that BI is just E1 intersection, well, E1 is kind of empty event, right? But still, E2, E3 intersection, well, E1 is the full event, right? It always happened. EI, right? This is just a complicated way of saying of that. I'm just saying here is that the second pole did not, sorry, the second value x2 does not collide with x1, and and so on until the ith value. Right? The ith random variable did not collide with the previous I-1 choices. By the way, I'm going to speak about, I should maybe before going any further, because I'm going to use this language. So let me speak, let me define this problem this way. So people like to speak about balls and bins. Right. So the idea is that you have n bins, in our case, m bins, right? Bin 1, bin 2, bin m. And then you have the balls, right? You have the first ball coming in, and you throw it randomly to one of the bins, right? Think about this routing and queue application I described. Right? It's exactly this, right? Then another ball shows up, the second ball, and you throw it somewhere, and so on, right? So then you can think about this problem as the following question. I throw n balls into m bins. What's the probability? And for example, to say the question of what's the probability that all the balls fell in their own bin, right? There is no bin that contains two balls, right? That would be equivalent. So in our case, m, every bin is a birthday, and I want all the n people to have their own separate birthday. Okay. Okay, so I defined those two variables, EI and BI, right? Now, if you think about BI for a second, we said that BI is just the intersection of E1, E2 to EI. In particular, you can write it as the intersection of BI minus 1 intersection with EI. Right? Okay, why is this useful? Well, we can speak about, we want the probability of BI. Right? The probability that all the balls are distinct. So I can write it as the probability of EI intersection BI minus 1. Right. Now I'm going to use conditional probability, right? So this is probability of, let's see, probability of EI given BI minus 1 divided or multiplied. Oops. Multiplied, right? Yeah, let me write it again. Okay. So this makes this, if you think about this formula, it just follows from the definition of conditional probability, but it also makes a lot of sense, right? Because it just says the probability that all the balls are distinct, fall in distinct bins, is a probability that the first I balls fell in the distinct bins, right? And if this happens, then the last ball have to fall in its own distinct bin, right? And the reason why we did it is because, as I mentioned, the event EI by itself is hard to analyze, but this event is, of course, very easy to analyze. right? Because what is this conditional probability? This is the probability that the first I-1 balls fell in their own bins, right? So if you think about the bins, right, think about it just as an array going all the way to M. We have I-1 locations that are occupied, right? Those are the I-1 locations that are used by the first I-1 balls. And those are exactly I-1 locations because we assume that Bi-1 happens. And now I ask, what's the probability, right? This is I-1 locations that are occupied. So the number of unoccupied locations is M minus this, which is this, right? So now I'm asking, what's the probability when I throw in the ith ball, it falls in its own empty bin? Well, there are M minus I-1 empty bins, and there are M bins. So this is the probability of this happening, right? And this is just 1 minus I-1 over M, which by the lemma is just E of exp of minus I-1 over M, right? Okay, so let's go back to the previous formula now. All right, this was probability of EI given Bi-1 times probability of Bi-1, right? This we just argued is smaller than exp of minus I-1. Yeah, over M, right? Times PB of I-1, right? And now I can apply this formula repeatedly, right? So this is going to be smaller equal than exp of minus I-1 over M times exp of minus I-2 over M, and so on, right? Namely, if I write it, this is just equal to the product of going k equal 1 to I of exp minus k minus 1 divided by M, right? And now we just need to do some algebra. It's not too difficult. Product of exp can always turn into summation, right? This is why we are always doing this silly trick. Right? And if you think about it a second, this is just exp of k choose to, okay. I just used here the fact that this summation is really, this is just 1 plus 2 plus k minus 1 divided by M minus, right? So the sum from 1 to k minus 1 is exactly this, right? And you get this formula. Okay. So what is this probability? This is the probability that all the birthdays are distinct, right? So going back to our example beforehand, so this is so claim. Let me just state the claim we got for x1 and x to xn. Independently distribute picked from from M the probability they are all distinct is, as we just said, smaller than exp of minus minus n choose 2 and 1 over m. Right? So that's what I just proved above. Now let's look at it a bit, because this is kind of confusing or surprising, right? So this this thingy written here, this expression is exactly the expected number of collisions, right? And essentially it says that the probability that they are all extinct, that there are no collision, is e to the minus the number of, is at most e to the minus of this number of collisions, in particular for what we got before, which was n28, right? 28 people and m equal 364. This probability was smaller than 1 over e, right? So not only we expect to have at least one collision, the probability that there is no collision, in a group of 28 people, there is no birthday collision, is smaller than half, essentially, which is kind of nice. Okay, so that's the birthday paradox. And I should say, by the way, that this estimate here of the lemma, this is an upper bound on the probability, but it's a kind of a very good estimate. So it's very close to the truth. Okay, questions about this before I move on to other topics? Please ask a question, I beg you, so I don't feel like I'm talking to myself more than usual. Okay. So okay, so that was the birthday paradox. Okay, so now I'm going to speak about the occupancy. Occupancy is essentially the same problem, but it's essentially the standard name for given to this problem. So occupancy problem. Okay, so we're going to be throwing n balls into n bins. Okay, so a natural question is to ask, for example, if we look in a bin, a specific bin, right? What is the number of balls in the first bin? You know, I'm picking the first bin, but it can be any bin because they're all symmetric, right? So we are throwing n balls into n bins. On average, we expect every bin to get one ball, right? So this is one. So this is the intuitive argument. If you want the more formal argument, so let's think about it. The more formal argument would go like that, right? So let xi be 1 if ith ball fall into first bin. Right, so it's an indicator variable. Since there are n bins, right, the probability of xi to be 1 is of course 1 over n, right? The expected number of balls in the first bin is of course just the sum of the xi. And this of course is bilinearity of expectation. The expectation of xi, which is just y over n, of 1 over n, so that's 1. Right. This is just in case you wanted the formal argument. Okay, so this is not very surprising, right? But we can ask a natural question, right? What's the probability that we get a lot of balls in the first bin, right? Or any specific bin. We look on a bin and we ask, what's the probability that this bin has a lot of balls, right? And the intuition is that we somehow don't expect bins to be too full. So in particular, one can prove the following. Well, I'm going to prove the following. And I think this is the first time we're encountering a strong concentration. So with probability larger than 1 minus 1 over n, when we throw n balls into n bins, no bin has more than so let's see. So 3 ln n divided by ln n. Okay. Right, so no bin would have more than this number of bins, number of balls. I should say that this is an interesting bound because as you would see later in the course, once you know all the tools and so on, without thinking, the expected bound is off log n. So if you want ln n, right? The ln n is what you expect as an upper bound because of, as I said, standard tools that we'll see later on, like Chernoff inequality and so on. And what this theorem says is that, no, we can do better. We get this log n and the denominator, which is, surprising. And in fact, this phenomena, later on when we speak on Chernoff inequality, we will revisit this phenomena because if you use Chernoff inequality in the right regime, you get this. The proof of this is tedious calculation, but I think it's still useful to see them. So I'm going to do them. And hopefully it will be useful. Okay, so what we are going to do, we are going to just we're just going to write explicitly the probability of this bad event, compute the probability, then bound it, and then sum it over all the bins and get our bound, right? So we'll start with the question of what's the probability that a specific bin gets exactly eyeballs. Okay, so this is not very difficult, right? Because you can think about the probability. We have probability P, which is when we throw a ball to fall into the bin, right? And we are doing this. We are throwing n balls, so we are just doing. You're doing this experiment n times. So this is just a binomial distribution, right? So this is the binomial probability of getting eyeballs into the bin. So, and this is exactly n to the I, p to the I, 1 minus p to the power of n minus I. Right? So this is just because it's a binomial distribution, right? This is so small, I'm just going to ignore it. Right, so it's n choose I times 1 over n to the I. oops, let me zoom in, n to the I over 1 over n to the I. Okay, and now I'm going to use this lemma, right? The lemma that I spoke about earlier. That tells me that the I binomial coefficient is bounded by this. It's really easy to remember, right? Because for the upper bound, it just says, you know, you make it into a fraction, and then you pay an extra e, right? So let me maybe write it in nicer form. Okay, so this is this times 1 over n to the I, and now you just cancel things out, right? This is just e over I to the power I, right? Okay, so this is an upper bound on the probability. Okay. Okay, back to our purposes. Right. So we want to, let me see J. Let me call it CK. Yeah, CK would be the event that the first bin, all the bins are symmetric, so I can just pick the first one. Bin has K or more bars, right? So now I can just bound it, right? So probability of C of K, well, it's just the sum of the above probability, right? It's sum I going from K to N, right? I'm going for I to N to ask what's the probability that I have exactly I balls in this bin, but we bounded it by above by e to the I to the power I, right? Okay, and if you think about it a second, think about K as being large. K is definitely larger than E. In fact, let's take K to be larger than 2E, right? Just to clarify the summation. So if we start the summation with 2E, you know, that this fraction is going to be smaller than 2, than half, right? Because I is larger than 2E, this is smaller than half. So this summation behaves like a geometric summation, right? With the terms shrinking by a factor of 2. So in particular, this is just smaller than twice the first term in this summation, which is just E over K to the power K. Okay. Okay. Okay, and now we just need to compute the value, right? So let's do that. That is where the fun kinds of, this is where the computation becomes kind of tedious. So we're going to take K to be C ln N over ln N, right? We'll say the constant. I'm not going to do the computation too precisely, right? Because life is too short. But the class notes have the exact calculation, by the way. So we have this, right? So by the above, the probability want is smaller than this expression. And now we just need to, this is 2 to exp of what? E to the K is just K, right? And this is minus K ln K. Right? And now all you need to do is to realize that K here is much smaller than this if K is large enough. Or more precisely, if N is large enough, right? if k is larger than 10, then ln k is something like 3, and then minus k ln k is larger than k, right? So this is, in particular, would be smaller than t2exp of minus k ln k divided by 2, right? And now you just put in the value, right? So it's not very enjoyable, but let's do it anyway. So c ln n divided by ln n. This is the value of k. We have 2 here. That's fine, right? And then we need to take the ln of this, ln of c ln n divided by ln n, right? Now, the important thing to observe is that what's written here, let me maybe use a different color. What's written here is essentially, oops, ln n. This is roughly ln n, right? Well, this is roughly ln n, and when you take the ln of it, you get this whole expression is roughly ln n. Okay, up to some small constant that don't matter, and as such, you can just cancel things out. So essentially, this cancels with this, right? And as such, again, n has to be sufficiently large. So this is really smaller than 2 of exp of minus c ln n. Here I'm using double quotes because one has to do the exact calculation with the constant, which I'm skipping here because it's too tedious. But in particular, this is smaller than 1 over n squared, right? If c is sufficiently large, c larger than 6, let's say, right? Or in particular in 3, if you do the calculation more carefully. If you want the calculation more carefully, you can see the class notes. Okay, so what does this mean? This means that, let's go back in time to try and reconstruct what the hell we were trying to prove. C of k was the event that the first bin had more than this, more than ln n over ln n balls, right? And we just argued that this probability is smaller than 1 over n squared, right? So the implication is that we have n bins, right? This is C of k. This is an upper bound probability any bin contains more than, what was it, 3 ln n over ln n bars, right? So I just used the union bound, right? I have n bins, a probability that any one of the bins have more than this number of balls at most 1 over n squared. So this is just n times 1 over n squared, which is at most 1 over n, which proved the theorem. Right? Okay. So that implies that no bins contains more than ln n over ln, more than log n over log n balls. And essentially, you can go through the calculation I did. I bounded it from above, but you can do the bounding from below. And if you do this, you would get the same, up to a constant, you would get the same result. Namely, with very good probability, in fact, there is going to be a ball that have roughly log n over log n balls, right? So, which is kind of strange, right? Because you don't expect it, so if so it's a bit surprising, right? Because it somehow says that you're throwing n balls into n bins, and for n large enough, there's going to be a bin that gets quite a bit of balls, quite a reasonable number of balls, which is kind of surprising. Okay, questions about this? Okay, so this calculations were a bit tedious. I apologize. I hope you didn't all space out, or maybe you all spaced out. It's okay. It's part of listening to a lecture, I guess. But what I want you to take away from this is that one can, with doing elementary calculation, prove that when you throw n balls into n bins, no bin contains too many balls. And by too many, I mean this log n over log n bound. That's what I want you to take away from this portion. Okay, questions? Anybody there? Any questions before I move on? By the way, I hope that now you see the applications for routing, for example, right? Because it tells you already that if you have enough pins, you have a router and it can throw things into queues, and the number of queues is sufficiently large. Intuitively, this is not what follows from the calculation, but really that's what they imply. What the calculation implies that no queue would be overloaded by too much, even in the worst case, right? So it's kind of good. It says that things are going to be pretty evenly balanced across the queues or the servers, just by doing this random partition of the jobs, which is good news. Okay. Now, so I want to mention something. We will prove it later on in the course, but it's really a beautiful phenomena. So I want to tell you about it. Okay, so as I said, I didn't prove it, but as I stated, the above is tight, right? You throw n balls into n bins, there's going to be a bin that have ln n over log n over log n balls up to some constant with good probability. So the question is, can you do better, right? Now, the problem in the process that we did when you throw balls into bins is that if we randomly chose a bin that already have many balls, we have no recourse, right? We just have to throw the ball there, right? So a natural approach is to try and do something, right? You throw a ball into a bin, but if the bin is too full, do something else, right? So it turns out there are a lot of different ways to do it, and they're all kind of equivalent, and they're all pretty powerful. So the pair of two choices says, okay, when you throw a ball, choose two bins, choose randomly two bins, and then throw the ball into the bin that is emptier. By emptier, I mean have fewer balls, right? So it turns out that if you do this, one needs to work hard to prove it. So it's not fun, but it's a nice process, nevertheless. One could prove that the number of the maximum load drops from log n over log n to log n, right? This is a dramatic improvement, right? Why is it a dramatic improvement? Think about n equal to something like 2 to the 20, right? Which is just a complicated way of writing 10 to the 6 roughly, right? It's a million, right? So what is log n? Log n is going to be roughly 20, right? So you get over log n, but still it's fine. It's going to be maybe 7, right? On the other hand, log n is going to be something like 4, right? So it really is it really creates a big difference, and if you do a simulation, you get it. It's a real phenomena, and it kind of makes sense, right? It really says something very natural about life in general, right? If you have options, if you have more than one options, you can avoid doing something bad, right? You can always choose the alternative that is better than the other one, and that already can improve the situation. Now, of course, the question is, okay, if picking 2 location helps, what about choosing 3 and 4 and so on? It turns out that it doesn't help that much, right? It does help, but not by that much. I don't want to do the exact bounds because we will, as I said, we'll do a full lecture on it later on. So there is a benefit, but it's small. The shocking thing about this is that, in fact, you don't need to choose the other location randomly. So this is completely mind-boggling. It turns out that the following process is enough. You choose a location, and then you look on the location just to its right. Right? You look on the bin, and you look on the bin to its right, and you put the ball in the bin that has empty, smaller number of bins. If they have the same number of bins, you put it in one of them arbitrarily. It doesn't matter. Right? So you, in fact, here you don't even use more randomness, right? And it turns out that the same bound holds, which is very surprising. And again, it kind of gives you the intuition that having options is good in life. So, okay. So as I said, we will talk about it later on in the course. I just wanted to mention it because it's fun for the right value of fun, which might be not very high for you, but that's okay. Okay, let's do one calculation that is easy to do just because it's easy. So what's the probability of all balls right? So I'm throwing n balls into n bins, and I'm asking what's the probability that they all fall into their own bins, right? So yeah. So we can do exactly the same calculation we did before. In fact, we can use the bound we used before. So I thought that we are going to do something more interesting, but no, right? So I proved that the probability of this is smaller than this, right? And this, of course, is this is, of course, smaller than exp of minus n minus 1 over 2. So it's an incredibly small probability. You can also explicitly write the probability out in this case because it's n factorial divided by n to the n, right? Which is, of course, this is an upper bound, right? So, because why is that n factorial? Well, there are n ways of putting n balls into n bins, and there are n to the n ways of putting n balls into n bins. So, so that gives you this. Okay. That's a bit boring, but okay. Okay. So much for this problem. The next problem is a different problem, but it's kind of a fun problem too. Coupon collector. Maybe I should change the color. Okay, so here's the game. I don't know if any of you, this is like something from the good old days. Even in my time, it was fading out. So think about collecting things like cards, right? Like in the US, I think it was baseball players, right? So the idea is that you can buy a card, right? But you don't know which card you buy, right? So there are those, all the players in the league, right? So there are, let's say, N players or N cards. Okay, I'm going to call those cards coupons, right? So, and then you go and you buy a card, right? You might get a card when you buy something else, right? I guess in the good old days, you would buy a package of cigarettes and you will get a card or something like that, right? I guess nowadays for kids, you would buy a package of cereal, right? And there will be some toy in the package. Anyway, you go and you buy a coupon, and you randomly get some coupon out of those N coupons that there is. But of course, you want to collect all of them, right? You want to collect all N coupons. Okay. So the natural question is to ask, how many coupons do you need to buy until you're guaranteed to have all of them? Okay, and let's assume you're not allowed to use eBay, right? Because nowadays, what you would do, you would just buy, you would just buy probably all of them from somebody in eBay that sell a collection of all of them, and save your time. Okay, so not cheating with eBay. So the question is, how many coupons do you need to buy? And the amazing thing is that, as we will see in the next lecture, I'm going to prove some stuff in this lecture, and some stuff would be in the beginning of the next lecture. The amazing thing is that this process is very strongly concentrated, right? So you essentially need to, there is this very small intervals of number of coupons you need to buy, and with very high probability you have all the coupons. And if you buy fewer coupons than this threshold, then with very high probability you don't have all the coupons. So this is kind of pretty amazing. This is again a phenomenon of concentration. So, and the trick, one of the reasons why this problem is nice is the analysis is simple but clever, right? So we're going to define a variable xi, which is going to be number of coupons you buy till you get the distinct coupon. Okay, so this is not very clearly defined. Let's try again, right? So you buy the first coupon. The first coupon you get, of course, is unique. You don't have it, you're very happy, right? So X1 is 1. You bought one coupon and you got one. Now you start the second round, right? You want to get the second distinct coupon, right? The second coupon, you don't care which second coupon you get, as long as you get a coupon that is distinct from the first one, right? So maybe you're extremely unlucky and you buy a second coupon and it's identical to the first one. You buy a third one, it's identical, but somehow this is 1, 1, 2, right? But luckily for you, in the third round, you got a different coupon. So this would be X2 equal 3, right? And we continue in this fashion, right? Essentially, Xi is, since the time you have I minus 1 distinct coupons, how many coupons did you have to buy until you get I different coupons? Okay, so this is this error. And clearly what we're interested in is the sum of those variables, right? Why? Because this would be I going from 1 to yeah, I guess I defined it slightly different in the notes. That's okay. Of xi, right? Okay, so this is going to be the total amount of time it takes you to buy everything, right? And now I'm going to prove a lemma. Or maybe I should just do the calculation directly. So let's think about x of I. What is the expected number of xi, right? So xi is what? We already collected I minus 1 coupons, right? So the probability we pick a coupon we don't have is this, right? Sorry, the number of coupons that we don't have is this. As such, a probability of success is this, right? Okay, let me try to repeat this. The ith era begins when we have I minus 1 different coupons, right? And now the probability that I buy a new coupon is exactly the number of coupons that I don't have. All the coupons have the same probability, right? So the number of coupons I don't have yet is n minus I minus 1. I should, by the way, put a parenthesis, right? Very important. This is number of coupons I don't have yet, and you have to divide it by n. So pi is the probability of that I pick a coupon, a new coupon that I succeeded. If I didn't succeed, I repeat, right? So xi is distributed geometrically with n minus I minus 1 divided by n, right? And to remind you, the expectation of xi, since the geometric variable is 1 over the probability of success, which is, of course, n divided by n minus I minus 1, which is, of course, 1 1 I minus 1 over n. No, something is wrong, right? Where did I do a mistake? Yeah. The denominator is the wrong denominator. Thank you. I was like, what? Yeah, okay. So we get this, right? Okay. So now, if we want the expectation of x, this is the expectation of the summation of the xi, right? The total number of rounds we need to play. This is the sum, linearity of expectations. 1 plus I minus 1 divided by n minus I plus 1. Okay. So this is n. We can take the 1 out, right? And we can write it as I going from 0. I guess I go from 1 to n minus 1 of I divided by n minus I, which is just n. We can just flip the summation, right? So it's n minus I divided by I, right? N minus 1, it's important. Yeah, this is true, right? Just replace I and n. And this is, of course, just n, well, smaller equal than n plus n times the harmonic sum. Oops. So this is just n plus essentially n ln n. Okay, as an upper bound, right? Okay, so that's the expectation. Questions about this? Except for my stupid calculations, mistakes. Okay. So now we can also compute the variance. The variance requires some more work. So the variance of x, this is a variance of a sum of independent variables, right? This is really why we did it, right? We did it, we used the xi because the xi's are independent, right? Which is kind of very nice, right? It's like the time it takes you to the number of rounds you have to play to get the I distinct coupon, and the number of rounds you need to from there to get the I plus 1 coupon, those variables are independent. And variance of a sum of independent variables is the sum of variances. So the sum of the xi's. Okay. And you repeat this, some kind of tedious calculation, which I don't want to do because I'm too lazy. I'm just going to copy the thing from the notes. It's each one of the xi is a geometric variable, so we know exactly what its variance is. You plug it in, you do the calculation, and you get that this is n squared sum I going from 1 to n of 1 over I squared minus NHN. Okay, now I'm sure you all remember that the sum of 1 over I squared is pi squared over 6, because what else can it be? So that implies that this essentially is equal to, this term is roughly n log n, right? So n squared is much bigger, so this is roughly pi squared over 6 times n squared. Okay. Which is kind of nice. Why is it nice? Well, that implies that the standard deviation of x, this is the square root of the variance, right? This is going to be square root of this quantity, right? So it's going to be square root of pi squared over 6 times n squared. So it's pi, roughly, because we are doing some, so assume n is large enough so that it's a good estimate. It's a pi over square root of 6 times n, right? Okay, why is this interesting? Well, the number of rounds we needed, right, was n log n, right? To n log n in expectation, after n log n, n ln n steps, we collected, that was the expected number of coupons, that number of rounds we needed to collect all the coupons. And the standard deviation is n. It's smaller by more than an order of magnitude. It's smaller, it doesn't have the factor of n log n. And now we could just apply Chebyshev inequality, right? Because Chebyshev inequality tells us that you cannot get too far away, right? So formally, the probability of x to be larger than n ln n plus n, this plus n is to just, to avoid various noises, right? So because we had the harmonic number, so the sum of the harmonic number is ln n plus small constant and so on. So it's definitely going to be smaller than n log n plus n. And then we just take t times the standard deviation, right? So t times n times pi over square root of 6, right? And this is, let's apply Chebyshev inequality. Chebyshev inequality, it says that probability of x minus expectation of x, right, to be larger than t times the standard deviation. This is smaller than 1 over t squared. Okay. So that already says that the n ln n is going to be the truth, right? We might be n ln n, and then a few, a little bit, maybe a few more n's away, but we're thinking here about the case where ln n is pretty large, right? N is huge, ln n is large, so so this is already a good probability. What I'm going to show in the next lecture is that in fact this can be replaced by something exponential in t. So the concentration in fact is even stronger than that. It's really very strongly concentrated. But that would be in the next lecture. That's all I wanted to cover today.